So, before we get started on graphing ourselves, we are going to take a look at the parent function for rational functions. Now, the parent function is just 1 over x. This is called the reciprocal function. Looking at this function, what shapes this graph? What are the two key features that shape the lines of this graph? The asymptotes, right? We have a vertical asymptote here along the y-axis and a horizontal asymptote through the x-axis. Always, 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 you should be drawing your asymptotes with dotted lines. You need to actually draw the asymptotes. Now, what is the domain of this function?
All real numbers. It's not equal to 0. Yeah.
Right. So it's everything, you're right, everything except for 0. And it's easiest to do this type of domain in set notation with the squiggly brackets because we just have to exclude 0 and be done. What about the range?
Y does not equal 0.
Good. Y such that y is not equal to 0.
Why do we need the such that?
How I've always thought of set notation is kind of like a sentence with a subject and then defining that subject. So it's like you're saying, I went running. The I is who you're talking about, the went is the such that, and then the running is what you're doing. It's the definition. It's just the accepted notation. I know, it's kind of funky. All right. Where or do we have x-intercepts, y-intercepts, or extrema?
No.
No. Now what does extrema mean?
Min and maxes.
Yes, your local min and max and your absolute min and max. What's another word for local? Starts with an R. Oh, no one knows?
Relative.
Relative, yes. Relative. And then what's another word for absolute? Starts with a G. Global. Global. Good. Do we have increasing or decreasing intervals here?
Yes.
Now I'm going to tell you, there's only one, increasing or decreasing, which it's always decreasing. Because remember, when we're talking about increasing and decreasing intervals, you always read from left to right. So reading from left to right, we are always going down. We're always decreasing. So there is no increasing. But what are our decreasing intervals? Good. Now, increasing and decreasing intervals, you do always need to write these in interval notation because they are intervals. Now, what about end behavior? Let's talk about the left end first. We always have to talk about
As x nears 0, x nears infinity, y nears 0.
good. As x approaches negative infinity, y approaches 0. Now, from now on, do you remember what notation I told you should write end behavior in? Limit notation. Good. It's not really that much different from our normal end behavior notation. All that's different is we write an LIM for limit. And then below limit, we write what x is approaching. So on our left end, x is approaching negative infinity. And then as x approaches negative infinity, what does our y value approach? 0. So I say f of x equals 0. And yes, it is now an equal sign. This is because the limit is 0. That's like the boundary. It's not what your y value is approaching, it's what is the boundary. What is the limit?
What would it be normally if y did cross? It'd just be near 0.
I don't know what either of you were asking or answering, so that works. All right, what about the right end? How can we say that end behavior? So the limit as x approaches infinity of f of x is 0. And like I told you before, you're going to be using and learning about limits nonstop in calculus. Discontinuities. What discontinuities do we have? What asymptote? So, remember way back when I described discontinuities to you, I said a discontinuity is when you're tracing your pen from left to right and you have to pick up your pen to continue. Does the horizontal asymptote ever force you to pick up your pen? Only the vertical asymptote forces you to pick up your pen. Technically, horizontal asymptotes are not discontinuities. So, the only discontinuity we have here is x equals 0. What else could be a discontinuity besides a vertical asymptote? A hole. Good. A hole. And is this function even or odd? It is odd. Why is it odd?
Because it parallel because it has rotational symmetry and not the origin.
Symmetric with respect to the origin. And what would make a function even? Someone I haven't heard from. What would make a function even?
If it was symmetrical with respect to the x or y axis.
The y-axis, yes. Symmetric with respect to the y-axis. This is not to be confused. This concept is not to be confused with an even or odd degree. Right? Even or odd degree is just based on the biggest exponent's even or oddness, right? Whereas an even or odd function is based off its symmetry. There's a difference. Any questions on this review over our parent function? All right, you guys go ahead, and I want you to try to remember how transformations work. I want you to try example 2. Write down the transformations for A and B. So let's go ahead now and try to sketch the graph for part A. Knowing that there is, can someone go up there and hit the sweet button? I think it's over there, yeah. Good. Okay, so knowing that there is a translation down 1 and a translation left 2, what do we think about moving down 1 and left 2?
The origin?
What's on the origin? What?
The asymptotes?
Yes, the center of the asymptotes. That's what you think about moving. So from the origin, I'm moving down 1 and left 2 to create the new center for my asymptotes, which, like I said before, we absolutely need to draw with dotted lines on our graph. Now, what's the only other piece of information we have?
The stretch by 7.
Vertical stretch by 7. How do I use this to actually draw the lines, the curves of my graph?
Does the vertex go more towards the vertical asymptote? I don't know, the lowest point of the curve.
Yeah. So what happens is the center of your curve moves further away from your origin, right? The center of your asymptotes. But how do we actually graph points given a vertical stretch of 7? What do you do?
Well, in the parent function, it at 1, 1, there's a perfect point there.
Mm-hmm.
So
Nobody knows?
no one knows. It's just more squished towards the origin.
No,
It's more
not towards the origin.
more squished away.
Away, but how? How do you graph these points?
Oh, you plug them in.
No?
Wait.
I mean, you could. You could always plug in. If you're ever confused by graphing, please do. I don't mean to yell for that. Please do plug in. But if you have a vertical, okay, think of this.
You realize we took algebra 2 in COVID, right?
Yeah. Okay, if you had a quadratic that has a vertical stretch of 2, what do you do to get the rest of the points?
Oh, you.
Square root at every or square at every.
Yes? Okay. I guess you guys didn't graph very often last year, did you?
No.
If you have a vertical stretch of 2, all you do is go up 2 over 1. And then you have the mirrored image as well. Boom, you have your graph. What if you had a vertical stretch of 4? What do you think you'd do?
Up 4 over 1.
Oh my gosh, you go up 4 over 1. And then boom, you have your graph. Same concept here. Same concept with every function if you have a vertical stretch. Instead of going up 1 over 1, where are we going to go?
Up 7.
Up 7 over 1. And because everything is symmetrical, you also are going to go to the right 7, up 1. And boom, you have the curve. And then again, because everything with rationals is symmetrical, I'm also going to go to the left 7 and then down 1. And then from the center of my asymptotes, down 7 to the left 1. 1, 2, 3, 4, 5, 6, 7. And then we have our sketch.
It's crazy.
What if we had a vertical stretch of 6? What would you do?
Same thing, but say 6 instead of 7.
Right. You go up 6 over 1, left 6, down 1. Okay. I don't think I need to show you sketching part B, do I? Because there isn't even a vertical stretch. It's just, well, I guess I could do it real quick. It's just down 5 and then to the right 3. 1, 2, 3, 4, 5. 1, 2, 3. That's the center of your asymptotes. And then how do you create the curves of your graph? You just go up 1 over 1. And then down 1 over 1. And that is the center of your curve. And we're done. Any questions there? This one? All I did was move the center of my asymptotes right 3 and down 5. And then because there is no stretch, our perfect points are always up 1 over 1 from the center of our asymptotes. Okay. So now, just a few more things I need to teach you, and then I'll let you do your homework.
Woo.
Which is that?
Oh, is this? I've drawn Spider-Man on it.
All right. So I know that this graph is crazy, and I don't really love it because technically, where is our horizontal asymptote?
What the hell?
Yeah. This, I feel like, was done incorrectly. So we're just going to pretend that y equals 0 is our horizontal asymptote, okay? We're going to pretend like that line does not go below the x-axis. So our horizontal asymptote is y equals 0. Where are our vertical asymptotes? X equals 1 and x equals -4. Where is our removable discontinuity?
On the point -3.5.
Yeah, that's what I would say. I hate, again, another reason why I hate this graph, we're not given the equation and our hole is in a perfect point. So can we accurately say where this point is?
No.
No, we have no way of doing it. So we are going to have to make an educated guess, which I just hate. But we should in math be able to make an educated guess. All right, so now we get into the fun part. We're being asked to write the end behavior and the behavior approaching the asymptotes. So this right here, as x approaches positive or negative infinity, this is end behavior.
Would it be y approaches 0?
But we're going to write it in limit notation. So we have two ends, one on the left and one on the right. The one on the left is going to have x approaching 1.
Negative.
I think I'm going to pull sticks. So as x approaches negative infinity, over here on the left, as x approaches negative infinity, what does y approach, Monica? 0. So we say, in limit notation, f of x equals 0. And then for our right end, what does x approach, Miriam? Yes, x approaches positive infinity. As x approaches positive infinity, what does y approach, Ane? Yes, again, it approaches 0, so the limit of f of x is 0. None of that should be new to you. What is new is understanding what's happening at the asymptotes. So, remember when we were going over rationals in standard form, what creates the vertical asymptotes? The zeros of the what?
Function. I don't know.
If I had this, guys, if I had, yes. If I had this, what creates the asymptotes?
Oh, the denominator.
These zeros of the denominator. So I have one asymptote at x equals 1, and the other at x equals -4. Now, you notice how the one at -4, we're approaching that -4 from two directions. And notice how approaching it, they're kind of split. This means the multiplicity of that 0 is 1. When they're split like that, the multiplicity is 1, or it's an odd number. If they go up the same direction, like they are for 1, what that means is we have a multiplicity of 2, an even multiplicity, when they go in the same direction. Now, we need to be able to describe the behavior approaching these asymptotes. Notice how you can approach the asymptotes coming from two different directions. You can come from the left or you can come from the right. Let's look at which one does it want first? The -4. Coming from the negative direction, so coming this way, towards our asymptote, what's happening to the y value?
Approaching infinity.
Positive infinity?
Positive infinity. Oh, -4. My bad. I was thinking of the wrong asymptote.
So as we get closer and closer to -4, what's happening to the y value? It's going down, approaching what? Negative infinity. So we say, as x approaches -4 from the negative side. You see how I can't zoom in anymore.
Is that a -1 or just a minus?
So let me. As x approaches -4 from the negative direction. There's a negative in superscript. That's what that means. We're coming from the negative direction. As we approach -4 from the negative direction, our y value goes down, 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 down to negative infinity. So we say the limit as x approaches -4 from the negative direction of f of x is negative infinity. That's what this little superscript negative means. It means from the negative direction. And then also, we can approach coming from the right. So going from the positive direction towards -4. So going towards -4 from the positive direction. What is happening to our y value? It's going up, 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 up to what? Positive infinity. So we say the limit as x approaches -4 from the positive of f(x) is equal to a positive infinity. So now let's try it again on the other asymptote. As we approach from the positive direction, going towards 1, so as x approaches 1 from the positive direction, what happens to the y value? It increases. We're going up, 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 up to what? Positive infinity. So we say the limit as x approaches 1 from the positive direction of f of x is infinity. What about coming from the negative direction? What's happening to our y values? They're again increasing to infinity. So coming from the left, as x approaches 1 from the negative direction, we are still increasing up to infinity. I know there's lots of arrows on this graph. Any questions on the asymptotic behavior? All right, you guys try example 4. Now, could someone go up there and hit the sweep? Those are all correct. But hit the sweep because I have a point to make. I wanted you to get used to limit notation. However, when you are approaching an x value and the ends are diverging in different directions, like they are here, technically, there isn't a limit. you would state, if it asked you for the limit as x approaches -4 of f of x, you would say does not exist. Because it's not the same limit. It's not the same value of infinity or negative infinity. They're split. Only when they're going in the same direction like they are here does the limit exist. We are not, for sure, not going to get in depth about this because you do this a lot in calculus. This is not a pre-cal teak, but I did want to mention that technically, if the ends are diverging, you say that the limit does not exist because there isn't a single limit. There isn't a same stopping point. But again, I don't want to get too in depth about that. That's a calculus thing. All right, last thing I'm going to teach you. How, when we're in standard form, do you find horizontal asymptotes? Ananya, how do you find horizontal asymptotes? And do what with them? What acronym do you say in your head? Good. Bobo bots eats DC. Where you're looking at the degrees. Of the numerator and denominator. So, our first one, example 5. What type of horizontal asymptote do we have there? Do we have bigger on bottom, bigger on top, or are they the same? Bigger on bottom, so what does that mean? Y equals 0 is our horizontal asymptote. What about an example 6? Do we have bigger on bottom, bigger on top, or are they the same?
The same.
Exponents are the same, so what does that mean?
Divide the coefficient.
And what are our coefficients?
1.
So what is our horizontal asymptote? Y equals 1. Now, here's what I promised you I would teach you before break, but we weren't going to get into it before break. When you have bigger on top, what type of asymptote could you have? A slant asymptote. Now, slant, another word for it is oblique. This only occurs when the difference between the degrees is 1. So you notice here, 3 and 2, the difference between them is 1. You're going to have a slant asymptote, which is a linear line. Y equals mx plus b. What do you think happens when the difference is bigger than 1? Like here, the difference is 2. No, there is an asymptote. Think about it. If the difference of 1 makes a linear line, what does the difference of 2 make? A quadratic, or not technically a quadratic, but a parabolic asymptote. It's a parabola. What do you think a difference of 3 makes? A cubic asymptote. Yes. Are we going to make you graph these? No. But they do some crazy things to the graph. So, let's go ahead and find our slant asymptote. Do you remember how I said we find the actual asymptote? You divide them. You actually divide them. Can we use synthetic division to divide here? Can we use synthetic division? No. The only time you can use synthetic is when you just have an x and a constant. This is an x squared. We for sure, in the denominator, we for sure cannot use synthetic. So we have to use long division. This is why we review long division. We place the numerator inside of the house, and you place the denominator outside of the house. Do you remember what you do from here? Yes.
How do we do this?
Didn't I review this with you?
Yeah, probably.
Did I review it with you?
Maybe.
This was B Day had an extra day. Okay, I didn't review. I was about to get really mad. I'm like, I just taught this to you. No, I didn't. No, I didn't. Okay, so what you do is you ask yourself, what do you multiply the leading term x squared by to give you the leading term inside of the house, x cubed? X.
Wow.
Then you take that x and you multiply it back in. So you have x times x squared, which gives you, these should match. If they do not, you're doing it wrong. Then because we multiplied one term, we have to keep multiplying. X times x gives us x squared. And x times negative 6 is negative 6x. You subtract. You subtract these. So we have, and I like to put parentheses around all of it so I remember to subtract everything. We have x cubed minus x cubed, we get 0. If you don't get 0 there, you did something wrong. Negative 3x squared minus x squared is negative 4x squared. 3x minus negative 6 is 9x. Subtract a negative makes it a positive. And then we bring down the next term. And then we repeat the whole thing.
And then you go minus 4.
What do you multiply the leading term x squared by to give you negative 4x squared?
4.
Negative 4.
Negative 4. That's what I said.
Uh-oh. Then, what do you do next?
You do the exact same thing. You subtract everything.
Well, you multiply it back in, yes, and then you subtract everything. So, negative 4 times x squared is negative 4x squared. Negative 4 times x is negative 4x. And negative 4 times negative 6 is a positive 24. And then you subtract everything. Negative 4x squared minus 4x, negative 4x squared minus negative 4x squared cancels to be 0. 9x minus negative 4x is actually 13x. And negative 1 minus 24 is actually negative 25. Can you multiply x squared by anything to give you 13x?
No.
So what do you think this 13x minus 25 is?
Remainder.
The remainder. Do you remember what I said you could do when the remainder, I'm sorry, let me restate that. Do you remember what I said to do when we're finding the slant asymptote with the remainder?
Nope.
You ignore it.
Wow. So y equals x minus 4.
Yes. So our asymptote is y equals x minus 4.
What?
yes, you are going to have to remember how to graph a linear line. How do we graph this linear line?
Take the y-intercept. Just do y equals x and you move it down.
Move it down 2,
-4.
and then where do you go from there?
I remember pretty well. And then you go by 1.
Yes, up 1 over 1 because our slope is 1.
I remember Precal.
And then this is an asymptote, so you do a dotted line. And we're done.
So good.
You guys go ahead and do example 8. Find that asymptote on example 8.